Good afternoon. For those of you who didn't have a chance to come to the first two lectures, it's my great pleasure and honor to introduce Professor Charles Kane of University of Pennsylvania. And he is well known for his seminal contributions to condensed matter theory. What may be less known that Charlie is also a pretty good classic guitar player. And I believe it's not inconsequential for his work in physics, because his work is always find some new themes and finds harmony that other people either didn't see or couldn't see. And it's not like it happened yesterday or today. In the early 90s, mid-90s, works of Charles Kane and Matthew Fisher kind of infused new life into a, I would say, stale subject of one-dimensional quantum fluids, and became a burgeoning field. And actually, some of us were able to shine the reflected light emanating from the works of Kane and Fisher. And then later on, Charlie did it again with a forte by discovering topological quantum solids. And this is the field that kind of also combines in harmony an interesting and important field, subfield of condensed matter physics with a beautiful part of mathematics, which is topology. And that's this is still is living on, and Charlie is on the forefront of this developments. Also, I'd like to say that he also played a special role in my life. He was the first to identify for me the scent of the weed smoke, and it didn't happen here. You're walking on UCSB campus by some group of students, and I said, they smoke weed. And this is the first time actually that for me it was identifiable, because it was 92 and I was kind of fresh off the boat coming from USSR. So with that, please welcome.
All right. Thank you very much. So again, I'm really happy to be here again. And so this today I'm going to tell you about something that's completely different than what I talked about the last two lectures. So what I talked about before was topology in Hilbert space, and so that's where all of the great developments that we've had about topological insulators and most topological phases of matter. The interesting topology is really the topology of quantum states in Hilbert space. And the remarkable thing is that quantum states can be characterized by discrete topological numbers, and those topological numbers can show up in things that you measure. Okay, and so this is a very beautiful thing. And there are many, many versions of this story, okay? Particularly when you have symmetry and topology. We have the topological insulators, superconductors, crystalline topological insulators. These sorts of topological ideas also show up in metallic systems that aren't insulators. So for example, in a Weil semimetal, there is a Chern number associated with every Weil point. Okay, and so the same sort of mathematical ideas show up, in metals. So what I'm going to be talking about today is going to be about topology, but it's not going to be about topology in Hilbert space. Okay, and in a way, it's a much simpler and perhaps more trivial version of topology. And so Leigh said that I tend to notice things that people hadn't noticed before. So my superpower is to notice, curious features about non-interacting electrons that nobody ever thought was interesting. So this may be an example of that. So what started this for me was this epiphany that I had that the Fermi surface of copper, you can see this is like on cover of Ashcroft and Merman, right? And it's kind of like a fancy donut. Okay, so it has a topological number associated with it, just like a donut has a topological number associated with it. And so I started asking the question: does that topological number have any interesting or measurable consequences? Okay, and so I want to take you sort of through my journey thinking about this question. And so we've written a series of papers, and the simplest version of the simplest consequence that I'm going to discuss has to do with nonlinear correlations of the density in a Fermi gas. Okay, and so there's a very simple statement that I can make about this. And this is related to a deeper question, which is the structure of the quantum entanglement in a Fermi gas. Okay, and so this is something which this was actually the motivation for discovering these nonlinear correlations. But I'm going to tell the story out of order, and then I also have something to say about quantized nonlinear response as opposed to nonlinear correlations. And so I'll describe that. And then there's a related version of that, which may be a little bit more accessible in an experiment, which is to think about a novel kind of Josephson junction setup where it sort of gets at this topology of the Fermi surface. Okay, so this is work I started off doing this in the pandemic, sitting by myself in my room at home, but I had a PhD student, Pakman Tam, who joined in pretty soon after I started this, and he really played a key role in most of these developments. So he's moved on, so he's a postdoc at Princeton now, and also a postdoc at Penn. Christophe Dubulle, and also my colleague at Penn, Martin Klassen, played a role in some of these as well. Okay, so the Fermi surface is a topological object. It's characterized by some topological number. So let me first describe to you the topological number that characterizes the Fermi surface. So the natural mathematical characterization of the Fermi surface is a topological number called the Euler characteristic. And so let me just tell you what the Euler characteristic is. There's kind of a mathematical definition of it. It's the alternating sum of Betti numbers, if you know what Betti numbers are. But I think maybe for a physicist, maybe it's best to just sort of describe the specific examples in 1, 2, and 3 dimensions. So in one dimension, every Fermi Sea is just an interval. Okay, and it has 2 points, which are the Fermi points. And the Euler characteristic is just the number of components of the Fermi Sea you have, or equivalently the number of one-dimensional subbands that you have. Okay, so that's what the Euler characteristic in one dimension is. In 2 dimensions, what it is the difference between the number of electron-like and hole-like Fermi surfaces. So it's a little bit richer in 2 dimensions. So you can have an electron-like Fermi surface where the surface encloses the occupied states. Okay, so that's an electron-like Fermi surface. You could also have a hole-like Fermi surface where the surface encloses the unoccupied states. Okay, and those are distinguished by the sign of the Euler characteristic. So it's 1 and -1. If you have an open Fermi surface, then this one, you can't say whether the Fermi surface is enclosing electrons or holes. This one has Euler characteristic 0. Okay, and in general, if you change the Fermi energy, you can go through a topological transition. So if your dispersion of the energy has a saddle in it, then then you can go from from this situation to this situation to this, so you can go through a sequence of transitions. And these are sort of, this is well-known physics. These are called Lifshitz transitions. And, Lifshitz is an old guy. So these are things which have been, well known for a long time. But I think the thing that has been less talked about is what it is that, what is the difference between the states on either side of the Lifshitz transition. Okay, they're distinguished by some distinct topological indices. Okay, so in 3 dimensions, the Euler characteristic is related to the genus of the Fermi surface. Okay, so remember, for copper, it has these little handles. Okay, and the genus of the Fermi surface of copper is equal to 4. It has 4 of those handles, and so the Euler characteristic and the Euler characteristic is going to be a sum over all the components of the Fermi surface of 1 minus the genus. Okay. One other point I want to make just about this is that there's a distinction between talking about the topology of the Fermi surface and the topology of the thing that's inside the Fermi surface, the Fermi Sea. Okay, they're related to each other, but they're not exactly the same. So, for instance, in 1 dimension, every Fermi Sea has 2 Fermi points, right? Every interval has 2 ends. Okay, so they're related by a factor of 2. It turns out in 3 dimensions, they're also related by a factor of 2. So, the Euler characteristic is the thing that you get from the Gauss-Bonnet theorem. You integrate the curvature, you get the Euler characteristic, and maybe you remember the formula that the Euler characteristic of a surface is 2 times 1 minus g. Okay, and that's, again, this factor of 2. In contrast, in 2 dimensions, the story is different. Okay, because in 2 dimensions, every Fermi surface is just a circle. Okay, topologically, all of these Fermi surfaces topologically are circles, and a circle is trivial. Okay, it has Euler characteristic 0. So there's a difference in 2 dimensions between the Euler characteristic of the surface and the Euler characteristic of the interior. So there's, in a sense, in 2D, the Euler characteristic of the interior has more information in it. Okay, and it's sort of an even-odd effect. All even dimensions, the boundary is 0, and in all odd dimensions, it's twice the interior. Okay, so this is the Euler characteristic, and what I want to do is I want to try to first explain to you that this Euler characteristic shows up in something that you can measure. And it's very, and I'm going to start off by telling you something that it is almost trivial, okay? Which is just to consider a 1-dimensional Fermi gas. These, simplest thing, 1-dimensional non-interacting electrons. I fill my states up to the Fermi energy. And so what I want to consider is the equal time correlation of the density. So this is S of Q. This is the thing that you measure with X-ray scattering. Okay, so it's just rho of Q, rho of minus Q, and so this is a calculation you can almost do in your head, because rho of Q is just C dagger C, and you use Wick's theorem to contract the C's and the C daggers. And so what it ends up being is a sum over the momentum states that are inside the Fermi Sea, but at K plus Q has to be outside. So basically, it's exactly you're summing over the states that are in this interval of length Q. Okay, and so it's exactly going to be Q. Okay, divided by 2 pi. Okay, and so if you have 1 Fermi Sea, it's obvious you get 2. If you have 2 subbands, then you're going to get twice that, because you get 1 for each subband. Okay, and so in 1 dimension, S of Q is quantized. Okay, so it's Q over 2 pi times an integer. Okay, and one thing I'll say, this isn't just true in the limit that Q goes to 0. Okay, this is true. It's exactly true as long as Q isn't too big. Okay, so obviously if Q is bigger than KF, then it's going to, or bigger than 2KF, it's going to break down. Okay, But as long as Q is smaller than that finite amount, then this is really an exact statement. Yeah, it's going to be the same. The only thing that will change if you have some more complicated dispersion is what the precise cutoff where it stops being true. You know how big Q has to be for it to break down. If Q is small enough, it'll be exact, because it's always going to be measuring the length of an interval whose length is Q. Oh, you mean so it's going right through the bump? Then you're going to be then you're at the transition. Okay, so if you go very close to a transition, then the range of Q over which it is exact kind of goes to zero. And it makes sense that something like that has to happen, because what happens if you're exactly at the transition? Obviously, you're not going to get it. Yeah. So right. So look, if you're close to a topological transition, then the range of Q sort of is smaller. But if you're in the phase away from the transition, then it's valid for a finite range of Q. Okay. All right. Good. So again, this is a kind of a trivial statement, in one dimension. So it's I'm sure people knew this, they just didn't think it was that interesting. Okay, so but the thing which is a little bit more interesting than this is that this formula generalizes to all dimensions. Okay, and so let me tell you what the generalization is. So in 2 dimensions, I'm not going to consider the 2-point equal time correlation. I want to consider the 3-point equal time correlation. Okay, and so this is going to be a function of Q1 and Q2. So the Q's have to all add up to 0 if I have translation invariance, and so it's going to be a function of Q1 and Q2. And so what the result is that it's exactly equal to Q1 cross Q divided by 2 pi squared times an integer, where that integer is the Euler characteristic of the 2-dimensional Fermi Sea. Okay, and in 3 dimensions, there's a similar thing. Okay, in 3 dimensions, it is the 4-point equal time correlation function, which is now a function of 3 Q's, and it's the absolute value of the triple product divided by 2 pi cubed times an integer. Okay, and so now, so I originally stumbled on this formula in a very roundabout way. I was actually interested in something else. I was interested in the next thing I'm going to tell you about, which is the structure of quantum entanglement. So I'll get to that story. And we ended up sort of discovering this by numerically calculating this thing. Okay, and it was remarkably quantized. I didn't understand why, but I believed the numerics that we did, and so then I worked really hard and did some horribly complicated thing to prove that this was true. Okay, and it was only a year and a half later that I had an epiphany of that actually I should have known this. It should have been obvious. Okay, so let me tell you the reason why this is at least a little bit obvious. So there's a very simple argument which I can explain to you. Okay, and so let me try to explain this to you. So let's imagine that we were going to try to calculate this in 2 dimensions. So what would we do? So let me say, so what this argument is going to be is it is going to be a version of a very famous formula that goes back to Euler for that describes polyhedra. Okay, so if you have a polyhedron, you can count the number of vertices it has, the number of edges it has, and the number of faces it has. Okay, and there's this beautiful formula in geometry that says that if you take the number of vertices minus the number of edges plus the number of faces, it's always equal to 2. Okay, and that number 2 is the Euler characteristic of of a polyhedron that has which has the topology of a sphere. Okay, and that's why we call it the Euler characteristic. Okay, so it's kind of a version of this argument. So let me explain to you how this goes. So if we're going to calculate this 3-point correlation, you can imagine doing the calculation using Wick's theorem. Okay, it's C dagger C. You do the contractions. There's going to be 3 contractions. Okay, and each one is either going to give you the Fermi occupation function or 1 minus the Fermi occupation, depending whether it's C dagger C or C dagger. So maybe it's plausible you get something that looks like this. Now the thing is that there's going to be one sum over K, okay? And this sum over K, the argument of that is only going to be points which are basically points which are on the corners of the parallelogram, K plus Q1, K plus Q2, K plus Q1 plus Q2, okay? And so the way that we can organize this integral over K is to think of the integral over K as an integral over just one unit cell of this lattice times a sum over the lattice that's generated by Q1 and Q2. Okay, so so if it's just like if you have a crystal, the integral over space you can write as a sum over unit cells times an integral over just one unit cell. Okay, and so the thing is that so let's fix the I'm writing as an integral over one cell, and then I have a sum over the lattice. And so let's think about what this sum over the lattice is doing. So the lattice, what it is going to give me is it is going to give me so the occupied points in this lattice define a triangulation of the Fermi Sea. Okay, where these points, it's sort of like a discrete approximation to the shape of the Fermi Sea. Okay, and so now let's think about what this sum over the lattice points is going to do. So if you multiply this out, there's going to be terms with 1f, there's going to be terms with 2f's, and there are going to be terms with 3f's. So the term with 1f is just going to count the number of points inside this Fermi Sea. Okay, sort of like counting the number of vertices of a polyhedron. Okay, the terms with 2f's, well, they are precisely counting the number of links between points that are where both points are inside the Fermi Sea. Okay, so that's sort of like the number of edges, and the terms with 3f's precisely count the number of triangles. Okay, and so what we end up with is this number of points minus the number of links plus the number of triangles. And the beauty of this is that this is a topological invariant. Okay, you see, we still have this integral over K naught to do, and what that's going to do is that's going to make this entire lattice sort of slide, to the left and right. So some points are going to come and go. So this point will stop being inside. Okay, so the number of points will change, but notice that when this point goes outside, the number of points goes down, but the number of edges goes down by 2, and the number of triangles goes down by 1. So this entire sum stays the same. Okay, and so this is the theorem that this is a topological invariant. Now we can just pull that outside the integral because it doesn't depend on K naught. And so all we have to do is evaluate the volume of this parallelogram, which is Q1 cross Q2. Yes. It's not necessary. So if it's not commensurate, you need to refine the argument a little bit. So how about if you allow it to be commensurate with an arbitrarily large denominator rational number? Okay, so let's imagine that Q is a rational number times the size of the Brillouin zone. Okay, then what I can do is I can make, so let's suppose the denominator of that rational number is n. Then I can make n copies of the Brillouin zone, and then it will be commensurate with that. Okay, and so then and by doing that, one can recover this result. Okay, so So I can prove that as long as Q is any rational number, it's going to be okay. Okay, and since you know, I can always make a rational number that's close enough to any real number, then I think that's good enough for me.
Good enough for everybody in the room except
Yeah. Okay. So in any case, so I mean, look, this is something we thought about, and I think that's an answerable question. Yeah. Okay. Good. So I mean, if you think this argument makes it obvious, then it's obvious. Okay. So and believe me, this is much easier than what I did the first time. Okay. Yeah. All right. So now. Okay, and one other thing, it's clear that this can generalize to all dimensions too. So in 3 dimensions, we're going to have the number of points minus the number of links plus the number of triangles minus the number of tetrahedra. Okay, so this thing, and then it's going to be the volume of a parallel pipette. Okay, so this sort of is a general result for non-interacting fermions. Okay, so there's no interactions here. And so you might ask the question, what if you did have interactions? Okay. Yeah, Steve.
just slightly confused by this is the this is the volume of the Fermi Sea you're integrating over?
Well, I'm integrating over all of momentum space. So this sum on K is an integral over the entire Brillouin zone, but the F's are only non-zero inside the Fermi Sea. So in it's only the red dots, you know, so the sum in general is all of the intersection points here, but the only non-zero ones are the red dots. Yeah, the Fermi surface is the blue thing, and the Fermi Sea is the light blue inside. Yeah. Okay. So there's a question about interactions. Okay, and the short story is that the interactions destroy the quantization. Yeah, this is 0 temperature. Absolutely. Yeah. At finite temperature, you know, there's a singular behavior for small q here. It's an absolute value, and that gets rounded out at finite temperature. Okay. So what we've shown is that, you know, so for, you know, one dimension we have this, the 2-point correlation is quantized. Actually, in one dimension for free fermions, the 3-point correlation function is actually, it's exactly 0. Okay. And actually this, you know, should remind you of something. This smells a lot like bosonization. Okay. Because if you bosonize free fermions, then you have free bosons. Okay. And so this is just a statement of Wick's theorem for both. You know, this is the connected correlation function. So the connected correlation function for free bosons, since you have Wick's theorem, is 0. Okay. Now, but the thing is that if you turn on interactions, then you know that the density correlation function, density correlations in a Luttinger liquid will be modified by the Luttinger prime. Okay, so we still have this kind of singular mod q behavior, but its coefficient is no longer an integer. Okay, and so this is you know, this is true. You know, it's actually so we still have this is still true provided we have non-interacting bosons. But of course, you know, in general, the bosons, when you bosonize, are going to be interacting. It's just that the interactions are irrelevant. Okay, and so actually, if you have you know, if you have the Luttinger model, which is exactly linear dispersion for your fermions, then that maps exactly to the non-interacting boson model. Okay, but if you have any curvature to the dispersion of your fermions, then that maps to an interaction in the boson theory. Okay, so actually it's a little bit remarkable that this is true. Okay, because this is true even if there is a curvature. Okay, and so if you bosonized it, to get this 0 here requires a miraculous cancellation. Okay, but this is, I think this is a property that free fermions have. Okay, so yes, that's true. This is still exactly 0 for non-zero values of Q.
Except if Q must be less than 2πf.
Pardon?
The Q must be less than 2πf.
Yeah, no, it has to be small enough, but it doesn't have to be infinitesimally small. Yeah. So and again, but this is only true for non-interacting fermions. Okay, and we have the same thing in higher dimensions. So in higher dimensions, I told you we have this quantized 3-point correlation. In 2 dimensions, the higher density correlations are going to be exactly 0. Okay, for non-interacting fermions. But just like in 1 dimension, if we put on interactions, and in higher dimensions, the Fermi liquid parameters kind of play the role of the Luttinger parameter. Okay, and in fact, I think we understand how the Fermi liquid parameters will modify the this formula. Now, when I write this down, now I am taking the limit Q goes to 0, because once you have interactions, then you have irrelevant operators, and they're gonna modify things that they're going to give you, sort of higher powers of Q. Okay, and so but nonetheless, I think we understand that this 3-point correlation function will be modified in a way which we can understand by the Fermi liquid parameters. Okay, so the bottom line is that this beautiful quantized result is really specific to non-interacting fermions. Okay, now that said, I do believe there is a property that does survive with interactions in a Fermi liquid. Okay, and this was my original motivation for looking into this problem, which was to study the entanglement. Okay, and so I'm gonna get to that story in a minute. But once we have this result for non-interacting electrons, one can ask the question whether it's conceivable that one could measure it. Okay, so let's suppose we have access to a system with weakly interacting fermions. Could one do a measurement to measure these topological correlations? Okay, and so we put a little bit of thought into this, and so one possible way of doing this would be to measure the density correlations in a Fermi gas made out of cold atoms. Okay, and it turns out this is actually something that the cold atom people know how to do. Okay, so in particular, there's been a lot of progress over the last decade studying what's called the atomic gas microscope. And basically, what they can do is they can create a degenerate Fermi gas. It's in a trap, and they can basically take a picture of it, see where all the atoms are at some instant. Okay, and this has all the information in it. It has all the correlations. So we do this, take this picture over and over and over again, prepare identical states and take pictures over and over again and build up statistics. And so in principle, one should be able to calculate the density connected 3-point correlation function. Okay, so in principle, I think this is something that that can be measured. Okay, measuring it in real space. Okay, and then you can Fourier transform it to do it in Fourier space. And so just to try to demonstrate that this could be a feasible thing to do, what Pak and I did was just look at a simple finite sized system, sort of what was a 14 by 14 square lattice tight binding model, had about 100 fermions in it, which is sort of what the cold atom people can do. And it's a straightforward enough thing to just compute this this 3-point correlation function, in real space, for non-interacting fermions. Okay, and so that's what we plotted here. So what I did is I fixed R1 and R2, and I plotted it as a function of R3. And you can sort of see that there's correlation when R3 is along the same straight line that defined by R1 and R2. Okay, and that is precisely what this if you Fourier transform this singular correlation, what it describes is it describes long-range correlations where all of the points are along the same straight line. Okay, and that's sort of what you expect. What electrons do in a Fermi liquid is they kind of go in straight lines, right? And so it makes sense that the correlations should be all along the same straight line. So but the thing is that we can measure this in real space, and then we can do the Fourier transform, and what we see it has this absolute value of Q1 cross Q2 behavior, and looking at different Fermi Sea shapes, we can distinguish these different topological invariants. Okay, and so so of course, look, it's easy for us to do it on the computer. I'd like to say it would be easy for the experimentalists to measure this in the lab. I have to confess I'm a little bit naive about how hard this is for the cold atom people, and that's why I'm interested in talking to people about that. Okay, so but it seems like this to our naive eyes, it seems like this is a feasible a measurement that could be made. Okay. Yeah.
It looks like it's some analytical function of Q1, Q3.
Yes, it's the absolute value of Q1 cross Q2.
There's some is there any kind of
there's a long range correlation.
right? So
yeah, I mean, so think about it in one dimension, you have absolute value of Q. The Fourier transform of that is 1 over x squared. So that means there's just 1 over x squared correlations. Okay, and in fact, so what you have is these correlations that are where R1, R2, and R3 are on a straight line, and they decay like 1 over x squared, when they're far away from each other. So there's sort of a long range correlation, but they have to be on the same straight line. Oh, no, it's not Friedel. It's not yeah. Yeah, Steve.
You see directly the density and momentum space.
Right, but that's different than this, right? So I'm not measuring n of k, right? Because so I'm measuring. So yeah.
Thank you.
Yeah. Okay. All right. So we had one other thought about how one might be able to measure these correlations, and again, this may be a little bit naive, but so S of Q, that's what you measure with X-rays. Okay, you measure the density correlations. That's what X-ray scattering measures. And so the question is, could one do some sort of version of that to measure these higher point correlations? Okay, and so the thing that we have in mind here is to send in a pulsed X-ray, because I want the equal time correlation, so I want to take a snapshot. So I'm going to send in an X-ray pulse, and then there's going to be scattered waves which one can pick up, and usually what you would say is that S of Q is measured by the intensity as a function of scattering angle. Okay, and so if I measure the average number of photons at some deflection, that measures S of Q. Now, but if you have higher order correlations, then there are going to be correlations in the scattered wave. Okay, and this will lead to a kind of speckle pattern in the scattered wave. So in particular, if we think about the second order correlations, okay, so we can compute these second order correlations, and they depend actually on the square of S of Q, and the momenta have to sort of either be plus or minus each other. So when the correlations when Q1 is equal to Q2, that tells you that basically this thing is going to be fluctuating by an amount of order itself. So it's going to have a speckle pattern. Rayleigh, it's exactly that, Doug. Yeah, it's exactly, yeah. So that's what that tells you. But you see, there's a little bit more to it. There's going to be, so it turns out that when Q1 is equal to minus Q2, one also has this extra correlation. And so that means that the speckles at Q1 and at Q1, one scattering angle and then minus that scattering angle, there's going to be an extra correlation between them. Okay. Now that's not what we want. We actually want the third order one. And so this is going to be a correlation among three of these. And if they add up to 0, or plus or minus them add up to 0, then that actually picks up this universal 3-point correlation function, which we predict has this structure. Okay. So I suspect this is a tall order for X-ray scatterers to do. I know that they're interested in measuring these kinds of correlations, but I don't know whether or not this is going to be something which is feasible to do or not. Okay, but in general, I think the idea of measuring these higher order correlations, that's kind of an interesting direction to sort of learn what kind of information is in those. Okay, and so maybe this is a motivation for trying to do that. Okay, good. So now I told you that the reason I got into this story to start in the beginning was because I was interested in thinking about entanglement, and there's a long history of the interplay between entanglement and topological states. Okay, and going back to the famous work by Kitaev and Preskel, and also Levin and Wen, where they showed that if you have a topologically ordered two-dimensional state, and this is a much richer kind of state than the non-interacting fermions that I'm talking about. Okay, if you have a state that has a fractional quantum Hall state, or some state with a non-trivial topological order, then the entanglement can be characterized by the three-party mutual information. So it's sort of, so this is a quantity, it's a combination of bipartite entanglement entropies, which is designed so that all of the area law pieces, or the pieces that scale with the size of the boundary between the regions, they all cancel out. Okay, and so this mutual information, what Kitaev and Preskel showed is that mutual information tells you about a topological invariant which is called the total quantum dimension, and that's a quantized topological invariant that tells you about the structure of the topological order. Okay, so there's another way where entanglement enters into interesting states. If you think about gapless states, okay, if you think about a conformal field theory, then there's a famous result going back to Carty and Calabrese that if you have a conformal field theory, then if you divide it in two and compute the in a way, it's the two-party mutual information, but that's the same thing as the bipartite entanglement entropy, that it has a log divergence in the system size, but the coefficient of that log is a topological number, and in this case, it tells you about the central charge of the conformal field theory. Okay, and in particular, free fermions are basically the non-interacting fermions are the simplest conformal field theory you could have. And in that case, C is precisely the number of Fermi points you have. It's precisely the Euler characteristic. Okay, and so so what this led me to wonder is whether this could be generalized to higher dimensions. Okay, and in particular, you see the reason I like this, so one can calculate the entanglement entropy for free fermions. Okay, there's a well-known recipe for how you can do that, and what that calculation essentially amounts to doing is to computing the correlation function between the number of particles in region B and region A. Okay, and this is precisely related to this density correlation that I told you about. Okay, but remember, the density correlation depends on the interactions. Okay, but we know that the C does not. Okay, so in a Luttinger liquid, K, the Luttinger parameter, depends on the interactions, but C is equal to 1. Okay, even when K is not equal to 1. Okay, and so this entanglement entropy for a one-dimensional interacting Fermi gas state retains its quantized value. Okay, and so that was my hope, that I could generalize that. Okay, and so the first thing you might think is in a two-dimensional Fermi gas, maybe I should calculate the bipartite entanglement entropy. Okay, but of course that is going to have an area law. Okay, because it's going to scale with the size of the boundary, and in fact this is something that is actually, people have thought about what happens to this for say 2 or 3 dimensional free fermions. So basically you get an area law entanglement with a log correction. Okay, and so that's what happens, but that's not what we're interested in, because the coefficient of this, since it scales with the area has units, so that means the coefficient is going to have units, and so it's not going to be a topological number. Okay, so, and the problem with that is that the boundary scale, the size of the boundary, has a size. Okay, whereas in one dimension, the boundary is just a point, and that's the reason you get a universal number for a point boundary. And so what this suggests is that what we really would like to do is to characterize the entanglement, in 2 dimensions. 3 regions meet at a point. Okay, so if we can characterize the mutual information between 3 regions that meet at a point, then that'll be something that doesn't scale with the size of the boundary and could be a universal topological number. Okay, in 3 dimensions, generically 4 regions meet at a point. So this is, I realize this picture may be a little bit hard to parse. Think of it as a 3-dimensional peace sign. Okay, you can sort of imagine what that is, where 4 regions are touching at the same point, sort of just like what happened here. Okay, so this is what we set out to do. Now it turns out that there was an important reason why it didn't work in 2 dimensions. Okay, and I can explain that later if you like. But so let's skip to 3 dimensions. And so what I want to characterize is a 4-party mutual information between these 4 regions. And so one can define it like this, with this, it's this sort of sum where I'm adding and subtracting different combinations. So what SAB is, that's the entropy of the union of region A and B. Okay, and so one has all of these, and this is designed so that all of the area law pieces, all of the line law pieces, everything cancels out, and so all that's left is the intrinsic correlation among all 4 regions. Okay, and to calculate this, so for free fermions, there's a recipe for how to calculate the entanglement entropy. It involves using the replicate trick, and there's some technical details. But what it amounts to doing is it amounts to calculating this correlation function of the charges in the 4 regions. Okay, which is then just going to be an integral of the density correlations. Okay, and that integral of the density, and so that's the reason why I was interested in computing these density correlations, and I got this magic formula, which then I did the integral, and it turns out there is a universal log. It turns out it's log cubed divergence with a universal coefficient. Okay, and so then that translates then into this universal term for the mutual information. Okay, and so this is kind of a generalization of this Cardy-Calabrese result. Okay, of course it's only for free fermions, though once we did this calculation, we can then go back and ask what happens if we put interactions back in. Okay, and so because remember, in one dimension we knew that if we put interactions back in, we knew that they're not going to do anything because C stays the same. Okay, and so I went back and looked at this version of the calculation in one dimension, and I was able to understand why it is that the interaction corrections drop out. Okay, they had to, but I was able to understand why they drop out of the calculation, and then we could see that they drop out of this calculation for the same reason. Okay, and so we believe that this mutual information is robust to at least weak interactions, finite interactions. Okay, to having, so basically in a Fermi liquid, we believe that this mutual information remains quantized and tells you about the topology of the Fermi surface. Okay, yeah.
The 4-point function rho, does it still depend on structure?
Yes, it does.
This real space integral Q doesn't depend.
Well, no. This will still, this correlation function will depend on interactions. Yeah, it will. It's only when I calculate the entanglement. And, so one has to do, you have to do that calculate. So it's not a, yeah, there's a replica. You have to do the replica calculation to see why it is that the interaction terms drop out. Okay. But the thing is you'd say the same thing for the one-dimensional there's the one-dimensional version of QA, QB is going to be something times log of L. But that coefficient depends on the interactions, on the Lenger parameter. Okay, but when you do the replica calculation and get the entanglement entropy, then those interaction corrections are not present. Okay, so yeah. You still have what?
You have a quadratic problem. Interactions are reduced to the effective parameters of single particles, or?
Well, okay, so the way I thought about the interacting problem, so my view of how to think about a Fermi liquid, I learned from Shankar, which is that basically a Fermi liquid is a Fermi gas with RPA corrections. Right. Okay, and that basically if you allow all of the irrelevant operators to flow to zero, then the only thing that's left are the RPA corrections. Okay, and those give you the Fermi liquid parameters. Okay, so that is what? Well, RPA. I mean, so you're summing bubbles, right? Yeah, and there are different ways of saying. You could also, there are theories of how you would bosonize in higher dimensions, and then that amounts to it's a quadratic theory for the bosons. Okay, see you, Steve. So it's a quadratic theory for the bosons, and that is kind of equivalent to doing the RPA theory for the fermions. Okay, so So that's the level at which I did this theory. Okay, so I didn't do any fancy calculations with interactions, but I tried to use what I at least think I understand about a Fermi liquid, which is that when you've flown to the Fermi liquid fixed point, then all that's left are the marginal Fermi liquid parameters, and those amount to dressing all the density vertices with RPA bubbles. Okay, so yeah. There's probably a more precise way of doing this theory, but this is what I did. Yeah, Claudia. Well, the heat capacity also depends on the density of states, right? I mean, so it's not, the heat capacity isn't just C. Yeah.
Okay, because I thought you had the Luttinger parameter appearing in the 1D version.
Yes.
I noticed that you had F0, the Landauer
Yes.
parameter.
Yes.
Higher than.
Yeah.
But I wonder if it's kind of when you do the integrals to compute the entanglement, like that F0 exactly cancels, right? That whatever you got for the densities, the F0 is always disappearing, right?
Yeah, well, it is always in the entanglement. The F0 is always disappearing, and I could try to explain to you why the F0 disappears. The F0 is coming from summing an RPA series in a sense. Okay, the 1/1 plus F0 is summing the RPA series, but the thing is that in the replica theory that's not what you have. Yeah, so it's yeah.
But I forgot the F0 renormalizes one of the physical quantities in Fermi liquid.
Yeah, it's the compressibility. Yeah, that's right. Yeah, and it is, so the F0 does precisely renormalizes the density vertex. Okay, and so it makes sense that shows up in the density correlations. Okay, all right. Let's see, how am I doing? So basically, I'm out of time. Is that? Yeah. So I think maybe I'm not gonna talk so much about this quantized response. So let me just say that the first thing I tried, back when I was, decided to start looking for consequences of the Fermi surface topology. The first thing I realized, basically I tried to generalize everything I know about one dimension. Okay, and one other thing I know about one dimension is the Landauer formula. Okay, which is that if you have a one-dimensional ballistic conductor and you measure the two-terminal conductance, then it's quantized, and that integer tells you the number of one-dimensional subbands. Okay, and it's kind of like the integer quantum Hall effect. It's just not as good because you're not protected against backscattering. Okay, and so this relies on assuming that the transport is ballistic, so it has to be perfectly clean. Okay, so the question is whether there was some generalization of that, and I think what I'm going to do is I'm going to tell you about this thought experiment. Okay, and I think this is as far as I'm going to go. So the question is there a way I can generalize this quantized Landauer transport to higher dimensions? And so in order to do that, let me cast the Landauer problem in a kind of Laughlin-like argument. Okay, so Laughlin gave a beautiful argument for understanding the quantization of the Hall conductance in the integer quantum Hall effect. Okay, and so translating that into a one-dimensional wire, let me imagine I have a ring. Okay, and if I adiabatically thread a quantum of magnetic flux through that ring, then what's going to happen is there's going to be, Faraday's law gives you an electric field, so there's going to be an acceleration which moves every electron over by one space. Okay, and so after I thread the flux h over e, at the end I have one extra electron here and one missing electron here. Okay, and so I can diagnose that by counting the number of right-moving electrons and ask, how does the number of my right-moving electrons change when I thread a flux? Okay, and the fact that it changes is really a consequence of the chiral anomaly. Okay, and then that comes about because the right movers and the left movers, they're really connected to each other at the bottom here. Okay, and so so this is the argument that you have, for a one-dimensional, and the fact that I get exactly one electron here when I thread a quantum of magnetic flux, that's related to the fact that the conductance is precisely E squared over H. Okay, so so can I generalize this to two dimensions? Okay, and so let me give you a version of this argument. So now let me have a two-dimensional electron gas, which I can define on the surface of a torus. Okay, and so now I have two fluxes. Okay, and so what I want to do is I want to count the number of electrons that are kind of moving up and to the right. And I want to ask how that changes if I thread fluxes. Now, of course, if I add a flux in the x direction, then every state, for every value of ky, everything's going to move over by one space. So I'm going to have a whole bunch of extra electrons in this little sliver going around. Okay. So, but what I want to ask is, how does that change if I then thread a flux in the y direction? Okay, and you see, because most of these extra electrons, they don't really care if I thread a flux in the y direction. They're still going to be going wherever they go. These ones are not going to be going up and to the right, and these are definitely going to be going up and to the right, irrespective of what I do with the second flux. It's only the electron right around here that hasn't really made up its mind whether it's going up or down. Okay, that's going to matter. And so in the end, what we can compute is this sort of second variance of this number changing the flux in the x direction and the flux in the y direction, and that will be exactly 1 in this case. And that 1 is basically counting this point where the electrons are moving in the plus x direction. Okay. Now, in fact, this is measuring the Euler characteristic, because you can imagine a more complicated shape, Fermi Sea. Okay. And in that case, there are going to be contributions from all of these critical points where basically the velocity, the normal to the Fermi surface is in the x direction. Okay, but the thing is that there are two different kinds. There's the kind where it's sort of curving in, and there's the kind where it's curving out. Okay, and when you thread the flux in the y direction, they're going to have opposite effects in those cases. Okay, so you have to sum these with plus and minus signs, and it's not too hard to convince yourself that doing this alternating sum of these critical points precisely evaluates the Euler characteristic of the Fermi Sea. Okay, and you can sort of see it doesn't really matter if I was to pull this point out, so I only had one critical point, then I'd have 1 instead of 1 minus 1 plus 1. Okay, so this is the argument, and so basically what we were able to do is to turn this into a kind of so whereas this is related to a linear response Landauer conductance, this is related to a nonlinear second order nonlinear response. Okay, and basically it looks something like this. I don't want to go through this in too much detail, but there is a nonlinear response that is second order in the applied voltages. Okay, and one way of doing it is to have one voltage at omega 1, another voltage at omega 2, and then measure at the sum frequency. Okay. Now there are caveats associated with this. So this one has to think carefully about what the best way to try to implement this would be. And there are issues and problems with this that we could go over, but I think in the interest of time, I'm just going to skip that. And there's another version of this with Josephson junction, where I place one of the voltages by a superconducting phase difference. Okay, but again, I'm out of time for that. So I think we're just going to go straight to the conclusion. And the moral is that this Fermi Sea has a topological number, and this topological number has some consequences. Okay, and I think it's worth thinking about whether it's possible to make those consequences come to life in some experiments. Okay, thank you very much.
Questions?
Good question. Are there manifestations in the noise properties? There should be. Again, that's a correlation function. I have not been able to come up with a clean, property of the noise to measure. But that doesn't mean that I'm not so. There may be something there. I'm not sure I've thought of everything. So I think it may be worth thinking about that. Yeah, that's a good question. What are the consequences? Yeah, I'm not sure. Other than having this topological number. What's that? Well, I mean, so in principle, if one might be able to measure, I've been trying to come up with measurable property, measurements that one could make that would tell you about this. But if you're asking me, are these measurements interesting for any other reason than the fact that they measure this topological number? I'm not so sure about that. I will say that the story that I didn't get to tell you about the Josephson junction, there is something that is a little bit interesting. Let me just tell you what the setup is, because there is a consequence there, which may be kind of interesting. So the setup that I have in mind is to have a Josephson junction where I have superconductors which have a phase difference of pi, and they proximatize a two-dimensional electron gas. Okay, and so there's going to and so what this is like is it's sort of like a point contact for the 2-DEG, where instead of having an insulating energy gap that's pinching it off, I have a superconducting energy gap that's pinching it off. And so what we showed is that when the phase difference is pi, there will be Andreev modes that are bound to the junction, and one can measure the transport in those Andreev modes. So the setup that we have in mind is a sort of a 3-terminal device where we have the superconductors are grounded, the drain is grounded, we put a voltage on the source and measure the current that flows into the drain. And so the thing that's interesting about that is that what we predict is that it's sort of a rectifier. Okay, that when the and whether it's a rectifier in the positive or negative direction depends on whether you have an electron-like or a hole-like Fermi surface. Okay, and so maybe a rectifier is kind of interesting, and if you have a more complicated Fermi surface at positive voltage, it depends on the electron-like side. On negative voltage, it depends on the hole-like side. If you apply a AC voltage, then it precisely measures this this Euler characteristic. So maybe this rectification would be a maybe that would qualify as a consequence of this kind of analysis.
To clarify, it means that I was just thinking about you showed this image of the Fermi surface in the first slide.
Yeah.
And copper is a really interesting.
Yeah, no, I know, and I would love to come up with some interesting property that topological number enables, and that I'm not sure of. So I mean, look, I would love to be able to come up with a measurement that could measure the number 4 in copper. Okay, to directly measure that topology. So I don't have that yet. Okay, but I think if one could do that measurement, then maybe the most important thing about it would be that you can measure it, right? I mean, unless of course you could measure it. if, you know, look, the Hall conductance is the same sort of deal. It's a cool thing because you can measure it with quantized. Of course, with the Hall conductance, you can measure it to 1 part in a billion. And so that makes it, even more important. Okay. I doubt we're going to get anything that important out of this. Yeah.
Okay, so I think that maybe it's time to thank Charlie again.
Okay. Thank you very much.